Hi folks, I did a video segment earlier which talked about isostatic restraint. Now in that particular problem I had a bar which was pressure loaded at the two ends, a bar with a rectangular cross section which was pressure loaded at two ends, put it in a tensile mode. Now what this means is that these two loads, the pressure acting on the two faces in opposite direction, are causing a self-balancing load, and therefore in order to solve the problem with finite elements, we either have to use planes of symmetry, which that was not the intention, or to use the 1, 2, 3 rule, which Castillo also calls it the isostatic restraint. Okay, and we solved it. Okay. Now, there are some things that you have to worry about. We have to be careful a bit, though. So let me redo do a problem which is slightly different. So suppose we have a cube here, 1 by 1 by 1. That's just for simplicity. That's made out of steel. And now we're going to go and mesh it. Okay. We're going to mesh it with elements that size that you can see. Let's look at the mesh to see how it looks like. That's really not the issue here. Okay, let me change it to yeah, that was wireframe. That's why it looks like that. Okay, so let's deactivate this. Deactivate. By the way, what I would like to do, this thing is symmetric with respect to the XZ plane, but I also want to make it symmetric in this direction. So let me go ahead and actually do a pad instead of a mirror extend 0.5 so that we have symmetry also at the other end. It just makes it easier when we look at some of the calculations. Okay, back to analysis. There we are. Let me save this thing. File, save management. Save as, analysis, save as. We go desktop, new folder. Isostatic restraint. Subtle issues. Subtle issue. Okay, good. All right. So what I'm going to do is I'm going to apply a pressure on that face of, let's say, 100 psi. Tensile. Okay, so minus 100. Very good. Now, if I run the problem at this point, obviously this is going to bomb out because we don't have any restraint, and this is, think about it as a physical problem, this is going to accelerate. Okay, so for example, let's try it. It will bomb out. All right, and obviously, if you say show me the deformation, it's going to be rigid body motion. Okay, we don't have a control over it. It can be accelerating in a certain direction. It can be rotating, etc. All right, so let me deactivate this. The question becomes, obviously, the question becomes, what if I use the 1, 2, 3 rule? What if I use the isostatic restraint rule? What does that mean? For example, if incidentally I had a pressure on this face with the same magnitude in opposite direction, this is self-equilibrating, but here there is no self-equilibration. So let's try the isostatic. Okay, let's try the isostatic. What I want to show you is that it will work, it will run, but the question is, what does it mean? So let's run it. All right, let me plot the deformation, but I have to reset the scale. Where's the scale here? Reset the scale. There we are. Notice that it did run. Let's put it in the. It did run, but what happened? Look at this corner, by the way. What's going on here? All right, so let's do the following. First of all, let's also look at the stress. One means stress, and needless to say, there's going to be gigantic stress at that corner. Let's do a average ISO. Very good, and material shading. Okay, as we expect, because of the nature of deformations, you have a huge stress here. So what exactly happened? Deactivate this. All right. Let us look at which points actually were fixed by this isostatic icon. Let's see now. How was it? You go to Restraint. You say, show me Restraint visualization on the mesh. Okay, let's look at it carefully. You've got to look. It's kind of hard to find. In fact, because the mesh is so far. Right here. See that? Right there. 2 degrees of freedom were fixed here. It must be. Let's turn it around. Okay, 1 degree of freedom is fixed there, and probably at the other corner. Let's see, at the other corner in the bottom, 3 degrees of freedom were fixed. Right there, 3 degrees of freedom were fixed. Okay, good. So the question becomes, okay, physically, what happened? Because this block was subject to a load that made it, in principle, accelerate, but you know, what's going on here? So, well, first of all, if you try to find out what are the reaction forces at these ends, see that? It automatically created these restraints here, the 1, 2, 3 restraints. If you go here and say, okay, show me the reaction sensor, at this, it's going to refute. It says we can't do that. This kind of thing is not legitimate. So we can't have any information about that particular reaction. Okay, so let's do it a different way. First of all, deactivate this plot. Let me see now. This bottom corner, as you recall, this is just three restraints, and this is why it says clamp, by the way. Okay, I didn't do that. The 1, 2, 3 rule did it. Isostatic did it. So let me deactivate the mesh. Let's see now. Let's bring the part into the show mode. There we are. Okay, good. Let me see if I hide this thing. Oh yeah, I need to show it anyways. Okay, good. As a matter of fact, you can see what happens here. This is the 1. This is the 1, 2, 3. Excuse me. And the other one is probably 2. Okay, so let's go ahead and put a sensor here. But the sensor that I want to put in there is internal load sensor. See that? Internal load sensor. And select this face. Okay, now remember there was a clamp here, and I believe up there, where is this? Up here, I had 1 degree of freedom in the one in direction Y fixed. Okay, and then say update. Oh, so look at what happened. This face that I picked, on it, there is a minus 100 pound force applied. So basically this X component down here for this clamp is minus 100. Y is almost 0. Z is almost 0. Okay? Good. So it's self-equilibrated by selecting a point here. According to 1, 2, 3 rule, it applied all three, it fixed all 3 degrees of freedom, and of course, the body does not move as a rigid body anymore, and the reaction force there is minus 100. No force in Y, no force in Z. Okay. All right. Let's do another one. This is the one that I made. Well, first of all, let's make sure, let's find out where the other guy was. Let's see now. This was, oh, this is 2 degrees of freedom, right there. Okay, see that? One of them is in X, the other one is in Y. This clamp down here, we saw that the force in the X direction was minus 100. Now, okay, so let's try doing this internal force here. Okay. Sensor internal force on this face. Update. Okay. So in the X direction, there is almost minus 50. Y direction 0, Z direction 0. Minus 50. So let's see. This is the third, this is the one that is in the Y direction. So on this face, that fixing the X component due to the 1, 2, 3 rule creates a minus 47 pound at that location. Okay? All right. Okay, so right, this basically clarifies my caution. In other words, sure, the problem is truly a rigid body motion because you're taking an unrestrained object, you put a load on it, of course it accelerates in that direction. You can run it through the 1, 2, 3 rule and look at the stuff, but what's the meaning of that things? It's pretty much useless. Okay. As a matter of fact, let's do something else before we stop here. I want to show you the pressure distribution on this face. Okay, on this face, show the pressure distribution. Obviously, it should be all 100, but let's see what happens. Let's create a group, surface group. On this face, obviously, I applied a pressure of 100 psi, minus 100 psi. And now we're going to go activate the 1 meter stress and select the surface group. Okay. And don't show me the, just show me the material shading right here. Okay. So look, I applied 100 on this face, 1 meter stress. Okay. Actually, this should be very close to 100. In reality, that 1, 2, 3 rule is really throwing it up because it shows you that it's not. Let me show you that at least the principal stress should be 100. So let's deactivate this. Plot the principal stresses. And we don't want all of them. We want the one that is in this direction. Probably that's going to be C1, the largest one. So let's double click on this. Visualization. Just show me the surface group. Okay, show me the stuff in the surface group. Don't show me everything. Just show me the largest principal stress, which is your C1. Okay, and show it to me in the average isoform. Okay, you see, I applied 100. Now this at least is closer to 100, but still it's not going to be 100 because of those restraints. Those restraints that 1, 2, 3 put in there cause actually stresses develop, artificial stresses developing in the model. When the forces are self-equilibrium, self-balancing, like the previous video segment that I did, this won't happen. You apply the 1, 2, 3 rule. Those 1, 2, 3 rule, the isostatic does not impose additional stresses on the object. Okay, but here it does. So be careful. The 1, 2, 3 rule can be used in a very reckless way, or isostatic can be used in a very reckless way. And this is why when I do the course, I don't talk about this, because people think that the problem is running by putting this on pretty much everything. The problem runs, but it's wrong. Okay, unless they're extremely lucky, it's wrong.